So we have this question that says Jupiter is in a circular orbit around the Sun. Pretty close to true. Its distance from the Sun is about 5 times the average distance of the Earth from the Sun. The average, I think the actual value is 5.2, but 5 is close enough. And we want to know what's the approximate period of the planet, of Jupiter in terms of Earth years. Well, I know from Kepler's third law that I get a wonderful equation that relates the period of one object to the period of a second object to the radius of the first object to the radius of the second object. And if we remember this equation, I got to get my right values. It's t squared over period squared radius cubed. This equation actually comes from force is equal to mv squared over r, where the force is gmm over r squared. So I know that Kepler's law comes from this force equation. My velocity is not in a good format, but I know that in order to go around one full loop, I'm going to have a certain velocity, or with a certain velocity, it's going to take me a certain amount of time. So my time squared comes from here, and my radius comes from here, here, and there. So got my right values. Common to mix up these two values. But Kepler's third law says the period squared, the ratio of the period squared is proportional to the radius cubed, the ratio of the radius cubed. Got a little bit tangled up on my words. But what this says is that if I know one value, say the Earth, say T2 is equal to 1 year, and R2 is equal to 1 Earth radius, then T1 is going to be the time in Jupiter for Jupiter, and the radius of 1 will be the radius of Jupiter. So all I have to do is plug in these values, and I'm going to come up with my values. So I know that T1, T Jupiter over T of Earth squared is equal to the radius of Jupiter over the radius of the Earth cubed. And now I'm going to plug in my values. I know that this T Jupiter over T Earth quantity squared is equal to, well, the radius of Jupiter is 5 times. So I have 5 radiuses of the Earth over 1 radius of the Earth, quantity cubed, and I will see that my values of my radius of the Earth drop out. So this ratio, Jupiter to the Earth, quantity squared, has to be equal to 125. Or the ratio of Jupiter to Earth, the periods of Jupiter to the period of Earth, is equal to the square root of 125, which is equal to 5 to the 2/3, if I don't actually cube things, which just says that the period of Jupiter is 5 raised to the 2/3 times the period of the Earth. Well, 25 is 5 squared, 125 is 5 cubed, 5 is not 5 to the 2/3. I get a value, oh, that is wrong, 5 to the 3/2. Screwed up my exponentials. Square root is a 1/2, 3 was cubed before. Okay, so 5 to the 3/2. 5 to the 3/2 is a little bit more than, it's 5.15, so it's not quite 5 squared, but it's definitely larger than 5. So it's somewhere between 5 and 25, and my only answer that I get is 11.2. So if I actually look at this value again, I go back to my mistake, I just looked at the periods squared, the ratio of the period squareds is equal to the ratio of the radii cubed. Working out the math the right way, I got that my ratio of the periods is equal to the square root of 125, which is 5 to the 3/2. So this is a useful formula. You don't always have to go back to the full form of centripetal acceleration. But if you have two objects orbiting the same third object, in this case the sun, then we can use the ratios to figure out what our values are. This is actually used a lot in figuring out satellite distances in a lot of physics problems. Distance to planets, if we know how far a planet is away. So say we look at the demi-planet Pluto. Well, when we discovered Pluto, we could figure out how long it took to go around the sun. By knowing how long it went around the sun, we could figure out how far away from it is from us on average.